Welcome back, everyone. Hope you're doing well. Let's continue talking about vector spaces, but this time let's talk about vector spaces within vector spaces. You may have noticed that some of the vector space examples that we gave last time were actually subsets of some other larger vector spaces. For example, you may remember that we had this example from before that we were talking about CR inside of FR. You may remember that CR was the space of continuous functions with real, basically from the reals to the reals. And those fit inside of the set of all functions in the real numbers. Now, if you equip both of these with the same operations, which is just function addition and scalar multiplication, then these are two vector spaces, one of which sits inside of the other. The idea of a subspace that we're about to give is that whenever you have a vector space inside of a bigger one, as long as the two share the same operations, then you have what is known as a subspace. So for example, this C of R would be a subspace of F of R in that case. But remember that for abstract vector spaces, these things have to satisfy specific axioms. Here are those axioms one more time, which means that they have to have addition and scalar multiplication all defined to be the correct ways such that they satisfy these axioms here. Now, subspaces themselves are vector spaces too, but the idea is that the linear operations actually have to agree with for the subspace and the vector space on the big as a whole. So that's what is going to be kind of the separation here, is that we've had some things that are subspaces, quote unquote, but don't have the same linear operations. So we're not going to call them subspaces. They are just vector spaces in their own right. They do not get the same operations as their parent spaces, if you will. Just to kind of make sure that we're staying in our head kind of grounded, let's go ahead and see some examples here, like the ones that we just saw at the very beginning, where F is the space of all functions, C is the space of all continuous functions, and then C of R is the subspace of F of R. Here, the linear operations agree, and you have that C of R is a subset of the vector space R. And then we have the space of polynomials as well. We talked about how you can have the polynomials of degree less than, maybe less than or equal to n, whichever one it ends up being. Then if you have this, then this is a subspace of the polynomials. So the polynomials of degree less than n, we talked about at the very end, that was a vector space with respect to function addition and scalar multiplication. And so are the polynomials. So we'd say that Pn is a subspace of P. Now, how are we going to go through and show that some of these subspaces work is the question. And that's something that I want you to be thinking about as we go through seeing some of these counter examples. How do we prove things with subspaces? Are we going to have to go through and do all of those axioms again? Or if we are able to show that the addition, multiplication, and stuff work out very well, is there a way to make that process a little bit easier? Let's go ahead and see some counterexamples first so that we can know the limits of what it means to have a subspace. Let's take P to be the space of polynomials again. And this time, let's define a set P sub n, which is the polynomials of degree n, where n is some positive integer. Now here, these are just all of degree n. So what we mean here is that you have something like x to the n plus blah, 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 plus 1, but you don't have anything like x to the n minus 1. Like this would not be a polynomial of degree n. That's a polynomial of degree n minus 1. So this would not be included here. Notice, by the way, that that's different than how the set of polynomials was defined here for P sub n. That one we can show is actually a vector space. But as we're about to see, this P sub n star is not a subspace of P because it turns out that P sub n star is not closed under the operation of addition. Addition, remember, we said that is not well defined. And that's because we can take two things of degree n, add them together, and get something that is not of degree n. Here, we've given the options or the example of negative x to the n power. That is one example of degree n polynomial, as is x to the n plus 1, another example of a degree n polynomial. If you add them together, you get something that is degree 0. But remember, we said that this was a degree n polynomial, or had to be the space of degree n polynomials where n was a positive integer. This one has degree 0. And because of this, we have something that is not closed under addition. This means that P sub n star is not a vector space in its own right. So it cannot be a subspace. What about something that is a vector space in its own right? What about the weird example that we had at the near the end, maybe slide 21 or so of our previous presentation? Here we had R with the standard linear operations, that is standard addition and subtraction. Then you have R plus with the operations of the circle plus and the circle dot from last time. Now, R plus is not a subspace of R. Even though we have it being the case that the positive real numbers are indeed a subset of the real numbers, the operations between these two things do not agree. And because of this, we do not say that this is a subspace. Right here, this is not a subspace of R, even though we have an inclusion in between the two sets as they are. So what we mean by subspace is those two things, one that is actually a subset, and one that is actually a vector space. So these two counterexamples try and show you where one of those things could go wrong for each one. Okay. Of course, this has to have the linear operations agreeing as well. So if S is a subset of the vector space V, then we can go ahead and say, if it's a subset, let's go ahead and assume that it has those linear operations. Whatever it has from the vector space V, let's let S inherit that. However, in order for S to be a subspace, assuming that it has the same operations, it has to have two things, right? It's got to be a subset. We're already assuming that. It's also got to be a vector space in its own right. It's got to be a vector space in its own right. So the question is, how do we do that? And that's what the theorem known as the subspace test is going to be telling us about. The theorem known as the subspace test tells us that a subset of a vector space V, given all the same operations as the vector space V, is a bona fide subspace if and only if, remember that this means something unique. This means that you can go one direction or the other. Whenever you say if and only if, logically speaking, you're saying it's a subspace of V whenever, for example here, S is non-empty and closed under linear operations. But the idea is that you could also go backwards. If S, a subset of the subvector space V, is itself non-empty and closed under linear operations, you also know it's a subspace. So if you have a subspace, you know it's non-empty and closed under linear operations. And if you have a subset that is non-empty and closed under linear operations, you can go backwards and say that is a subspace. That's what we mean when we say if and only if. Sometimes you'll see me write this as IFF. This is meant to be the same thing. IFF to mean just if and only if. That's kind of like a kind of abbreviation, if you will, of what that is. And that's not a typo there. It's not double F. That just means it's if and only if. So non-empty and closed under linear operations. Let's make sure that we know that kind of how that works. Non-empty means something's got to be inside of it. Oftentimes the test here is to say that, is it the case that we get a zero vector inside of our vector space? Is it non-empty? Well, is something inside of there? Oftentimes it's easiest to check. Is it the zero inside of our subset? And I should be writing not V here, my apologies. I should be writing, or in a different color, should be writing S, my subset here. I'm checking to see that S is not empty. That's what's being meant right here. So is it the case that 0 is in my subset? Then I want to check to see if it's closed under linear operations. Is it closed under addition? Well, then that would mean that if you have two elements inside of your subset, then x plus y is in there. Can you have it be closed under scalar multiplication? Can you multiply it times anything inside the real numbers and get something there? So that's what we mean when we go through and do the subspace test. Now, anything that we try and say that we can use in this class, we're going to go through and try and prove. Let's talk about what each of these directions mean. Only if I will sometimes write like this. This is the right arrow, equals, and then maybe a greater than sign, if we wanted to try and like write it in terms of like how you would type it. So this is an arrow pointing to the right, a bolded arrow to the right. And what that means is that you're going to start from a subspace and try and say, okay, if S is a subset of V, if it's a subspace, so we're doing one direction of the implies here. If it's a subspace, then S is not empty and closed under linear operations. So we're going to try and go this direction. Well, only if ends up being pretty straightforward, actually, because if you have something that is a subspace, remember, it's a vector space in its own right. So if S is a vector space, well, it's got to have 0. So it has 0. And then it's also closed under linear operations because vector spaces have to be, right? So that is obvious. You already have, if it's a subspace, it's not empty, it's got 0, and it's closed under linear operations. So that one's good to go. Now, if is the interesting one. If is the one that says we can go from a subspace or a subset that is non-empty and close under linear operations and end up at something that is actually a vector space in its own right. Well, how do you show something's a vector space? We had to do that a lot in the last video, right? That was the one where we had to show it which satisfied A1 through A8, basically. Well, let's check to see which ones get satisfied. A1 through A8 are the ones that we have to check because we already know that the vector space is non-empty. We don't necessarily know that it's zero in there though, but we do know that it is closed under linear operations. That's the first thing that we have to check for a vector space, so we're already good to go there. We only need to show that it satisfies A1 through A8. Well, remember that S is a subset of V. V is itself a vector space, and because it has the same linear operations, most of the stuff is going to be there, okay? In fact, A1 and A2, A5 and A8 all come directly from the fact that S is a subset of V, which is itself a vector space. We maybe can call these maybe something called the universal axioms. These are the ones that start with for all vectors inside of S, right? Then, for example, commutativity holds. So whenever you have X plus Y inside of S, right? X and Y being members of S, well, they're also members of V. V is a vector space, so that automatically means X plus Y is Y plus X. So we automatically get commutativity, and that gives us a 1. And we can keep going through and doing this for each of the axioms that I have listed here. The only ones that we don't have this listed for are the ones that are more existential in nature. A3 is the one that says there exists an additive zero, right? Some sort of additive identity. Well, if I take a subset of a vector space, how do I know that that's going to be in there? How do I know I'm going to have a 0? And then 2, how do I know for every vector inside of there, there's going to be a negative version of it? So that's what A3 and A4 we have to go through and check. Let's check A3 first. Well, first of all, it is not empty, so we can take some X inside of this space, this set S. So we'll take a vector. Any vector that will work. We note that S is not empty, so this is something that's possible to do. That's why we need the non-empty nature in order to do this. We note quickly that the empty set is not a vector space because it does not have the vector 0. So take any vector inside of S. We're going to, again, have to show that S is a vector space in its own right, so we need to satisfy A3 and A4. Here's A3. We know that R times X is inside of this space, so we're going to make R equal to 0 for a second. We can do this for any R in the real numbers, and because of our use of quantifiers here, we know that we can just then make this equal to 0 times X. Well, what is 0 times X? We know from our previous video that that's equal to the 0 vector. So 0 is inside of our set. So 0 is an S. Great news. We've got 0. That's A3 satisfied. Checked. Good to go. What about A4? Now, we're again starting from any elements inside of our set S. And A4 is the one that says that for that element X, we want to show the existence of negative X. Now, negative X, we also proved last time, is negative 1 times X. So how do we get negative 1 times X to be in our set S? We take R to be negative 1. Take R to be negative 1, and that's going to be in our set S by our assumption right here. And so because of that, negative 1 times X is an S, so we get negative X inside of our set. That gives us A4. For all X, there exists a negative X, is what we just showed. So neat little thing that we did there. That should get us everything that we need and helps us prove the subspace test, one that we will be using more frequently than not to prove that something is a subspace of something else, because it's easy to check those two things, that your subset is not empty, as well as closed under linear operations. Those are the two things that we are going to want to show. Let's see some examples here of using this to show that certain things are subspaces. Let's take, for example, our kind of parent space to be R squared. Again, we're not saying what the operations are, so we're assuming addition and standard and scalar multiplication to be standard. Let's take the first one to be the line x minus y equals 0. We claim this is a subspace. What do you mean here? We're looking at the space of all x, y inside of our vector space V, but we're putting in a condition here. We're looking at the fact that x minus y equals 0. You may know this in different ways. You may know this as x equals y, y equals x. You may just know this as the place in which all of the the components x and y are the exact same for every single point inside of this. So, for example, this line consists of all vectors of the form t comma t, where t is in the real numbers. So all of those things are included inside of this set. Well, is this space closed under, is this not empty? That's the first place to start. Is it not empty? Well, yes. I can just plug in t equals 0. That works. So that gives me 0, 0. It's my 0 vector, in fact. So that gives me that. What else? Well, it turns out that I can add two things of these together and look at what I get. If I add two things where the first and second components are the same, then I get something where the first and second components are the same. That's exactly what it means to be a subspace, right? Essentially, you're saying that you can take two things inside of the space and add them together. In this case, you have two things where the x and y components are the same, and what you get is something inside of that set where the x and y components are the same. This gives us that this is closed under addition. We can also say that it's closed under scaling because if we multiply times any real number, the x and y components remain the same. It's closed under scaling. Now, here's a non-example of a subspace. What about the parabola? What about y equals x squared? This ends up not being a subspace at R. And you can kind of already start to see why. How would you add 2 points inside of the parabola to get another parabola point? Certainly wouldn't be the standard addition, that's for sure. So we can go through and try and find just one counterexample. Either a way in which maybe you find 2 points that are on the parabola that don't add to be in the parabola, because that would mean it's not closed under addition. Or maybe you find 2 points, or maybe you find a point such that if you multiply it times a scalar, that scaled point is not in the parabola, right? Either one of those is a good counterexample. Let's do a counterexample of each. Here are 2 points in the parabola. Here's 1, 1. That's when x equals 1. Here's negative 1, 1. That's when x equals negative 1. You plug that in, you get y equals 1 both times. If you add those together, you get something that's not on that parabola. Remember that when x is 0, y is 0, so it's not equal to 2. That is, 1, 1 and negative 1, 1 lie on the parabola, while 0, 2 does not. So this is not closed under addition. It's also not closed under scalar multiplication, although we don't really need to show this in order to disprove the fact that this is a subspace. It's not. So, but we'll give it anyway, just as another example. Here's 2 times 1, 1, a point on the parabola, and that gives us 2, 2. Remember, when x is 2, y is 4. It is definitely not 2. 1, 1 lies on the parabola, while 2, 2 does not. So this is not closed under scaling. So these are some examples and counterexamples in V equals R2. We could do the same thing for V equals R3, and I'll leave some of these to be checked for you. Z equals 0 is a subspace of R cubed. Z equals 0. This plane, what this means is, just being clear here, we are in the space of R cubed. So this is all x, y, and z coordinates, right? This is all the stuff in R cubed. But we are adding the condition that the z coordinate is 0. You can go through and check, is this not empty? Yeah, you can get 0, 0, 0. You can just make x 0, y 0, and that's good enough. That is an element where z is 0, so it is inside this set. So the set is not empty. However, it's closed under addition. It actually is. If you add 2 points where the z coordinate is 0, what's the z coordinate you're going to get? It's still 0. 0 plus 0 is 0. Same thing for scalar multiplication. So it ends up being closed under your linear operations. Hence, z equals 0 is a subspace. But the same cannot be said for z equals 1. You might already see why. If you try and add 2 things where z equals 1 together, what are you going to get? You're going to get 1 plus 1 equals 2. That's not in our subspace, because here we're saying that everything inside of this plane has a z value of 1. Notice that this is interesting geometrically speaking. We're taking the same object. Z equals 0 is like the xy plane. That's the one that stretches out in the x and y directions, but is just z equals 0 here. If you move it to where z is 0, then that means you have a subspace, because it's got the 0 vector. But if you move it to z equals 1, it's not a subspace anymore. Remember, all subspaces have to have the 0 vector, and z equals 1 does not, because for the 0 vector, z is actually 0, not 1. So this cannot be a vector space in its own right. And it also fails the subspace test for what it's worth, as we've shown. Here's another subspace. We don't have to consider planes. We can consider lines. Remember, the ways that we talk about lines in R3 are usually as parameterized equations. Here, we are just taking a vector like 1, 1, 0 and multiplying it times t. So like the points inside of here are the ones where x equals t, y equals t, and maybe z is 0. So for example, if you make t equal to 1, you get the point 1, 1, 0. If you make t equal to 2, you get 2, 2, 0. Stuff like this. This is one way to think about it. This is a subspace of R cubed. Kind of the same reason that the lines that we had in our square were subspaces. You can still add 2 points inside of here. You can still do scalar multiples. Importantly, however, we need to make it sure that the 0 vector is inside of this line. And it sure is. You can just set t equal to 0. But there's a different way to prove that this another line that we're looking at, which is the line 1, 1, 1 plus t times 1, negative 1, 0, is not going to be not going to be a subspace. This one is not a subspace. You can't just look at this and say, okay, well, this isn't 0, so this can't be the 0 vector. That doesn't work. Is there a t value that makes this equal to the 0 vector? I'm not sure about that because I'm looking at this z coordinate. Because 1 plus t times 0 gives me 1. Whatever my t value is, my z value is 1 here. That's never going to change. So actually, I'm kind of sitting inside of something like z equals 1 here. Interesting to think about that. Z equals 1 does not contain 0. So hence, this cannot be this fails the subspace test. It doesn't have 0 times any vector inside of it. 0 times that vector being the 0 vector. You also can do this in multiple different ways. You may have noticed that you can add all of the components of any point inside of here and get 3. Well, that plane does not contain 0 either. So this fails in 2 different ways. In general, a straight line or a plane in R cubed is a subspace if and only if it passes through the origin. Now, not only did we just say it's got to pass through the origin, and even then it may not be a subspace. We're saying that it actually is a subspace. This is an equivalent way of saying something is a subspace. Straight line or plane in R cubed is a subspace if and only if it passes through the origin. That's been kind of like our go-to for each of these things, so it maybe shouldn't surprise us. Let's see some more examples of subspaces here. Well, we've done a lot with looking at R squared and R cubed. What about R infinity? Well, here is some of the subspaces of R infinity. R infinity itself is a subspace of R infinity. You can include the space itself. This is included. This is a subspace of itself. Every vector space, in fact, is a subspace of itself. So that does work. What about L infinity? Little L infinity here is the set of bounded sequences. Excuse me. This is the set of sequences that are eventually, like they can't go any higher than this bar, they can't go lower than this bar, right? But that bound is arbitrary. It could just, as long as they are bounded eventually, right? So as long as they work that way. So the set of bounded sequences is going to be a subspace. You can show, for example, that when you multiply through a sequence by a number, as long as that sequence is bounded, even if you scale it by 2, it's still bounded. It's just bounded by a bigger thing. That's the idea of going through and showing this for this subspace. Converging sequences, same sort of deal. Say, for example, if you want to say everything converges to 5. If you add to it a sequence that converges to 6, what you get is something that converges to 11. Right? We know this from some of our limit laws back in going through Calculus 1, that you can add 2 sequences that converge to the same thing together, and that gives us what we want. Calc 1, Calc 2, that may be a Calc 2 thing now that I think about it. You can choose converging sequences, or even more specific, you can choose the ones that converge to 0. We can call those decaying sequences if we would like. So these are sequences that converge to 0. Notice, by the way, these are all sequences. So they're all subsets of R infinity, and they all get the same operations. You can add sequences together. You can multiply times anything. And namely, in order to show that these things are subspaces, we just have to show 2 things. If you have x sub n and y sub n converging to 0, what happens when you add them together? What happens when you multiply xn times a scalar? Is it true that that is also a sequence? Well, it's going to be. We can define adding and scalar multiplication of sequences. So those are going to be sequences. Is it true that they converge to 0 is the important point. Are they still inside of this space? Well, yes, if x sub n and y sub n both converge to 0, then so does x sub n plus y sub n. Actually, so does the scalar multiple. It all goes to 0. It's kind of like saying, okay, 1 over n goes to 0, but so does 1,000 over n. That also converges to 0. It just does it a little bit more slowly. So that's the idea behind these subspaces here. The set of summable sequences, right? You might be familiar with this from series. The series this looks like this, the sum as I goes from 1 to infinity of x sub n. These being convergent, you can add these sequences together. Again, this is a sequence because this is a sequence of partial sums, x1 plus x1, then x1 plus x2, and so on. You're just adding each and every other continuing x element to get the next element of the sequence. This being convergent means, okay, you're just continuing to add stuff together. The set of summable sequences is itself convergent. Absolutely summable is the same sort of deal. You have x1, x2, so on and so forth. If you keep adding these together and take this limit in absolute value, and if this is finite, then it turns out that this is also a subsequence. And you can do this using things like the triangle inequality to prove that, for example, the addition of these two things is going to be also finite in its absolute sum. And then we're going to have another set of sequences. We've been working a lot with the ones that have certain series or sequences or maybe convergent things, but we don't even have to think about convergence here. We could think about this. We could think about the set of real sequences that has specific properties to them. Now, sometimes we have to be a little bit more specific than maybe we prefer to be on these types of sequences. For example, here with r infinity naught, or r0 infinity, however that might be said. What we're saying here is that we're looking at the set of sequences, which are infinite, such that for all but finitely many indices, it's pretty much a zero. Basically, the idea is that there's only a finite subset of the sequence that is non-zero entries. So for example, 1, 0, 0, 0, 0, 0, and so on, just zeros at the end, like with a 1 at the beginning, that would be in R0 infinity. Here's one that would not be in this set. Something like this. This one actually has infinitely many elements, one like every odd entry, for example. This one is not inside of R0 infinity because it has infinitely many non-zero elements, right? So this is saying that this set of sequences is itself going to be a subset. You can add two things that have zero for all but finitely many indices. And even if the indices are different and when you add them, and still finitely many that are non-zero. You might even gain some zero entries when you add two things together. And same thing when you take scalar multiples. That's not going to change your set of non-zero entries in your sequence at all. So these are some examples of how we can make subspaces of each of these things, not only with the world of functions, not only with the world of Rn, but also with the world of sequences. All good things to make sure that we're keeping in mind, especially in the world of proving these things. But we've also not talked about matrices too much yet. We've given it as an example of a vector space. But matrices are something that we really want to be focusing on in this unit. What are matrices really? Well, remember that these are kind of just arrayed numbers put in some sort of form. Something like this, Aij, maybe where I goes from 1 and j goes from 1, maybe I goes to n, j goes to m. To say that we're working with n rows and m columns, for example. So here what we got is a system of linear equations. A good way to think about matrices here is to think of it as you're just taking systems of equations, much like this, and you're rewriting it a little bit. Let's say that we took all of these a values and plugged them into a matrix like this. And then we took all of our unknowns, our variables, and we wrote them as a vector, a column vector. x1, x2, all the way down to xn. So here's our matrix A, here is X. We could do the same thing with B, make that another column matrix. And if we do that, then what we're going to get here, if I change my entries to be I goes from 1 to M and J goes from 1 to N, just for size considerations, then I can write this as the equation AX equals B. Here, B is going to be this. That's this vector right here. It's B1, B2, all the way down to Bm. So this is that way of writing a system of equations as a matrix equation. One single equation, AX equals B, B being the vector of B1 through Bm as a column vector. So any solution, any x value here is an element of R sub n. You can just choose whatever those elements are such that they satisfy this system of equations. That basically just equates to plugging in a particular x vector inside of this matrix equation, saying, okay, we'll multiply that through by the matrix A. If you get out the vector B, then you're done. You're good to go. The question is, let's take all solutions of this system of equations. It's not necessary that there's only one unique solution here, or that there's any solution at all, in fact. This could be infinitely many solutions even. So the question is, with the system of equations, how do these solutions work together? Well, it turns out that in a very specific case, the solutions end up being a subspace of Rn themselves. And that happens if and only if all of the b sub I, everything inside of the b vector, is 0. That is, if when you write this equation out, you get that Ax equals 0. This is known as a homogeneous system of equations. A homogeneous system of equations. And that means that you are setting the system of equations so that all the constant terms in each equation is 0. It's a homogeneous system of equations. So think about what this means, right? We're saying that first things first, we're saying that this set is not empty, that there is actually a solution to this equation. Well, I can think of one. I can think of an equation, a solution to the equation Ax equals 0. What about x equals just the 0 vector? Well, anything times the 0 vector is going to give me the 0 vector, including this matrix A. So that's going to be something that makes this non-empty. I won't go too far into this. Instead, let's go ahead and take a look at the proof. Let's see how that sort of stuff works. We could even be thinking about, okay, how do we add things together? How do we multiply things together? But let's go ahead and say this is an if and only if. So there's a way to make this a little bit more clear. For example, if the solution is a subspace, then we know 0 is one of the solutions. And so what that means is that when 0 is one of the solutions, then we have to have that b is equal to 0. So if the solution set is itself a subspace, that means that x equals 0 is a solution because it's a subspace, so it's got to have 0 in it. And then we can just write a times 0 equals b, and then we also know a times 0 equals 0, and hence b must be equal to 0. That tells us that, for example, all of the entries in b have to be 0. That's exactly what we mean when we say this equations are homogeneous. So we have proven this direction. If something is a subspace, every b value must be 0. Now the if direction. If we have a system of linear equations, and this is equivalent to the matrix equation we've been talking about, Ax equals 0. Here we call A the coefficient matrix of the system, and the vectors here, all the column vectors like we've been writing them to be. Now, let's see if we can figure out if this is not empty. Well, we just talked about that A0 equals 0, so 0 is a solution. That means the solution set is indeed non-empty. What was the other thing we have to do for subspace test? Not only does it have to be non-empty, it also has to be closed. Exactly, be closed under the linear operations, addition and scalar multiplication. So here's addition for us. Let's say that we are in a homogeneous system. That's something we get to assume because now we're going the opposite direction. We're going from right to left. Our equations are homogeneous. So if Ax is 0 and Ay is 0, what happens? Well, then I can just take A and just multiply with x plus y on the inside here. That does work. A times x plus y is Ax plus Ay. I can just multiply that A out. That does work very nicely with our matrices. Well, since both of these are individually 0, each of these is 0, and if you add them together, then it turns out that x plus y also gives us that A times that vector is 0. That means x plus y is itself a solution. It's closed under addition. Then we have, if Ax equals 0, then if you do a scalar multiple of something, you can just move that scalar outside. Ax is 0. Any scalar times 0 is equal to 0. This means that Rx is also a solution. Think of it as like 2 times x, for example. If you have a vector such that Ax equals 0, then 2 times that vector will also plug in to give you 0. So the solution set is a subspace of Rn. So we've gotten a lot of good examples of subspace, and we've also got a lot of good examples about how to prove things are subspaces. In particular, we've got to test 3 things that we got to go through: non-empty, closed under addition, closed under scalar multiplication. Of course, we're assuming that it is a subspace with all of the same operations as the parent space. Okay, that should do it for today. Thank you so much. Have a wonderful day.